Hello everybody, welcome to another episode of New Heights with Bikash. As I say, I'm using Aalto University. So in Aalto University, we have this QCD labs called Quantum Computing and Devices Lab. And then we have today with us Aashish. Aashish is the doctoral candidate at Aalto University. Aashish, how's it going?
Hi, great, bro.
All right, welcome Aashish to the to the episode New Heights with Bikash. I would love to see your workplace, your workflow. How does your daily as a doctoral candidate? How does it usually go in terms of kike gardaichau, kasto gardaichau, and those kind of like let's have a bit of a discussion on that one.
First, let me thank you for choosing to do this. It's really an honor. So today is Saturday, and this for most people it's a weekend.
Yeah.
But for us, it's
Exactly.
a day
Every day you are
exactly.
looking into like different aspects, eh?
Exactly. Yep. So my usual day is typically look at a device. Physics wise, you design some design here. So something I have here on the screen. We'll get into detail of quantum computing later on, but this is just a layout of a physical device that we design and simulate, and then later on fabricate and do experiments on. So the first thing is come up with an idea, and that idea you would want to observe experimentally, and that requires few iterations from simulation and design back and forth. And once you have that, then you fabricate the device and you get something like this.
Okay. Quite small, eh? Really small.
It's a
it's
10 millimeter by 10 millimeter.
Okay.
And this is where quantum mechanics behave. I mean, from our high school, we've always learned that only atoms and molecules behave quantum mechanically. And here we have something that we can see with our own eyes. We can hold it in our hands and it still behaves quantum mechanically.
For general, I mean, just the general mindset, let's say probably it might be like a very cute.
So this is the same technology as the current transistor-based silicon microprocessors. So you use the same technology that people have designed and investigated for decades, and use that to explore quantum mechanical phenomena. And then
any rough timeline? Kati jasti लाग्यो होला Aashish? How long did it take to really actually make it the physical product?
So making this itself takes about a week.
Okay.
We'll later go on and visit the clean room where we do this. But the most time that it takes is in designing these devices and simulating these devices. It's one of the very heaviest simulation there is. It can take 2 or 3 days to simulate the whole design here. And once we are happy with the outcome of these simulations, then we go into the clean room and then we use this semiconducting technology to fabricate these devices.
Okay.
And that takes a week.
Okay. Did you mean simulation भनेको चाहिँ what does actually simulation mean?
So now these are electromagnetic circuits.
Okay.
So we simulate the electromagnetic properties, like how does electric fields behave in these circuits.
Okay.
What wiggly line you see here are called resonators. They resonate at certain frequencies, and that's the frequency we look in the lab. And if they are off by, let's say, few gigahertz, then we won't be able to see anything in the lab. So you have to accurately design this, and then you can go in the lab and look at that particular frequency.
Right. So there's a lot of calculations also behind.
Exactly. So we use, okay, let's not advertise the simulation software here, but we use commercial softwares to simulate these devices.
Okay. Yeah. Interesting. But yeah, so when we see you come to work and then you start looking into those, like what is happening, for example, to probably run few simulations.
Few iterations. Takes a week to really get some proper design ready.
Okay. So quite interesting. Yes. And so this is your table. What about how is the office looking?
Right. So we have in this office around 12 to 14 PhD and postdoctoral researchers.
Okay.
So PhD students are doctoral candidates here. It is typically for 4 years. You have to graduate within that time. At Aalto University, people are really strict with the 4-year timeline. And then you also have postdoctoral researchers. Okay. They join the group just after their PhD, and they continue this field of research. So that's one academic path you can take after PhD.
And how long does it postdoctoral does it kind of like takes many years, or is there a certain timeline?
It's a bad thing if you do it for a long time, because the next step in your academic journey would be to get a professorship.
And if you at the university.
at the university,
Okay.
or you can also go to, let's say, private or public research institute like VTT.
Ah, yeah, yeah,
Right.
exactly. VTT
So
has
then
like
you
a,
can,
yeah.
exactly. So you can go there and then do independent research for life.
Oh,
But
okay.
at universities, you have to do it for a few years before you get a professor position at
Mm.
any other university, either in Finland or elsewhere.
So sort of like the timeline is for first the doc,
Right.
then the postdoc,
Doc,
and
and
then
then the
based on that, whether you go on the university or the independent
right.
researcher, right?
And in this field, people also go to industry after their
Industry, yeah,
PhD,
exactly.
and
And
I
probably
think
come up with their own company and then
exactly, yes, yes,
kind of find their
right,
found their own
right,
company.
right,
Okay, interesting.
yeah,
Ani, we also see some sort of like a board as is there.
right.
What does it usually work? A lot of numbers.
A
Let's say
lot of numbers, lot of equations.
equations. Let's say
हजुर
बेला बच्चामा math पढायो, so
हजुर
we might पढ्ने बेलामा चाहिँ we didn't kind of
right,
look into, especially in the elementary and
right,
plus two गर्दा पनि त्यस्तो देखेको थिएन.
हजुर
But what does it usually kind of like, how does it on a regular basis, how much do you do these kind of calculations?
right. So whatever I showed you
Yeah.
were most of those things were classical. You can simulate using classical software.
Okay.
But the parameters that you obtain from those simulations, you plug into quantum mechanics equations, like Schrodinger equation is the equation that describes all of quantum mechanics. So you simulate those parameters, you plug those parameters in this equation and see what does what would the device behave like. And more often than not, things don't go as planned, right? So then there's a lot of debugging. So usually you will find few people here, not just one, and then you will throw the ideas back and forth,
And
try
you're just
to
like
understand
jotting
exactly.
down on the whiteboard,
Right.
eh?
So sometimes we use graphs to understand what are we doing here. Sometimes we look at the equations, and yeah, this is how we using first principle figure out what's not working, and how do we improve that.
Okay, interesting. And also about you're doing a lot of
Right,
research,
right.
playing with a lot of numbers and equations and stuff. How sort of हुन्छ नि, patented are these? For example, if somebody, a researcher
Right.
watching from, let's say,
Right.
UK बाट होस्
Right,
अथवा
right,
other rest
right,
of the
right.
world, can they look at the
See-
research and figure out, okay, they're actually working on this one? Can they do that?
They won't understand exactly the device
Okay.
wise, but these are standard equations of
Okay.
motion. This is the Hamiltonian, which describes the energy of a quantum system. So
Okay.
this you can find across devices.
Are you?
This is
Okay.
the same behavior you will see in atoms, molecules, or an engineered
So in
system.
a standard
Very
sort of
standard,
like
yeah.
equation.
So
Yeah.
from this equation itself, you won't be able to figure out what you are doing in the lab,
Okay.
but they will be able to understand what kind of physics you are simulating.
Sorry.
Yeah.
Foundation चाहिँ कस्तो हो भनेर they
हजुर.
can already kind of like
Right.
figure it out
That's
from
right.
here. Okay.
Yeah.
So kind of like a few people on a regular basis, just writing it
right.
down,
Yeah,
jotting it down,
yeah.
and maybe like taking it off and again trying iteration. I think
Right,
it's a lot.
right.
Research is so
Right,
much of iteration on a regular basis.
And that's the beauty of research, because in school, you have to do everything on your own, and you don't want to work together with your team in the hopes that they might do better than you. But in research, it's completely the opposite. And I have for a very long time not understood why school don't promote these kinds of teaching where you collaborate together and learn. I haven't heard of one single research where people independently have done PhDs. You have to work with a whole team. If you start a PhD in a university, you get an advisor and a supervisor. Supervisor is the professor, and advisor could be a postdoctoral researcher. And then together with them and other PhD students, you work on a single project and try to divide tasks according to skill sets, and then you come together to do the experiment and then later write a paper about it.
Exactly. And also I think in a lot of these kind of research papers, you have to base your findings so much on the findings that has been done in the past.
Exactly, yeah.
अब citation गर्नु
Right,
पर्यो.
right.
You have like probably hundreds and hundreds of citations, what somebody has said in let's say 1925 compared to what has been done on the same project or on the same topic in 1995, for example. So, and what has changed? So, you have to depend so much on the previous works also, and otherwise, the direct certainly exactly now, if you want to build something, I mean, some foundation has to be there.
And I totally agree with that. There is no new research as such. It builds based on what people have done in the past. And the field of physics we are exploring here was done in a completely different setting, for which they actually received Nobel Prize in 2016. Okay, don't quote me on that. I don't really remember the years, but people explored quantum mechanics in atoms and molecules. And using the same principle, we expanded that on a circuit, electrical circuit. Physically, they are completely different, but then you look at the quantum properties and they behave exactly the same. So you are right, there is no new research. You look at what people have done in the past and how can we use that information to build something new and advance the subject a bit further.
Right. And also like what we also discuss is, for example, when we're doing events, especially for example this Nordic,
Right.
let's say focusing on deep tech,
Yeah.
we also discuss a lot about from lab to the market.
That's
How
right.
much, Rick, for example, from your perspective about, you have been working on kind of research for quite many years, how kind of like how difficult it is to find the commercial model, like when
Right.
are you going to be ready to go to the market?
Right. Right. So usually it happens is that a research group usually is decades old or so. So they built ideas over time, and it happens. So if you have some new students coming in, they can take this idea further. Then you can take things into market. So for example, from our research lab, we have spun out two companies. IQM and QMIL is the new one. Right. So it's not that you will be able to generate ideas within the span of 4 years, which is the timeline for the PhD student, or 2 years for a postdoc. So depending on who is excited about bringing ideas to the market, you can have sort of luck that, okay, you happen to be at the right place at the right time to explore these activities. And that is what has happened in 2019, I think, when IQM was co-founded from here. They just had group of people who were motivated enough to bring their ideas to the market, and they did so successfully. And then 2024, which is this year, so almost 5 years later, then another group of researchers wanted to take their ideas into the market, and then they spun out another company.
I think it's also good, like I think we, like later on we will talk a lot about, of course, like the collaboration, for example, on different departments within the university, and VTT just here, and of course, like Aalto is just here, and they're spending a lot on the research space. Also, maybe like my question would be in terms of how sort of when the companies are, let's say, researchers are working so hard and then trying to create a company. Sometimes is there a competition between, let's say, VTT, competition between the Aalto, or like a different independent bodies, like, hey, we want to be the first one to really get into that kind of like a market?
Right. No, there definitely is. So that you can see already from two startups, IQM and Semicon. So they are built on different platforms, but they wanted to pursue that. So depending on what platform you are willing to pursue, they can choose their lane and not compete with each other, but survive together. So at Aalto University, we have decades, even half a century of research-backed ideas on low-temperature physics, which is what the current quantum computers are based on, at least in Finland. So we had a lot of know-hows. We had a lot of interdisciplinary research going on in the university that gave us the advantage to pursue this. VTT usually has small teams, so it is, well, I haven't worked for VTT, so I wouldn't understand what is their process. But from what I have known about this spinning out of this Semicon is that they wanted to pursue something different that has not already been done by Aalto. Otherwise, they would be competing within each other in a small country like this.
Exactly. But yeah, should we move then?
Yes.
What is the next thing on the agenda?
So I mentioned that we start with the design of the devices and then the fabrication. So we can go upstairs to look at our clean room where we do the fabrication. It's one of the largest in the whole Nordic.
Whole Nordics?
Yeah, that's right. And then now they are trying to expand that even further, probably making it, if not the biggest, then one of the biggest in the whole of EU.
Oh, okay.
So that's going to be called Quantinova.
Quantinova.
That's right. And so the Business Finland, or no, it's actually not Business Finland, but City of Espoo, VTT, and Aalto University. They are together coming up with almost $1 billion, I think, to expand this. So it will continue from here as we'll go up, and then it will. You've been to the parking lot at the back, and it will expand the whole area.
Okay.
So the
That's
idea is
quite a bit of commitment from.
right,
Of course,
right,
Espoo is like for the many years pushing it as kind of like a tech city, and then they're
right,
competing a
right,
lot, and they are also investing a lot in the in R&D at
right.
the back.
Right, that's true. I think I heard somewhere that Espoo is the Silicon Valley
Yeah,
of
yeah, yeah,
Finland.
yeah, yeah. They're
Right,
pushing a lot.
right,
I remember, like, because like in some of our events, Aalto or like Espoo City is one of our main
right,
partners, and
right,
they really push in, sort of like, especially in the deep tech aspect,
right,
especially in the research aspect. Like, hey, we are the city to
right.
be.
Yeah, so the idea was to build the infrastructure so
Yeah.
companies, it would be easier for companies to test their ideas, right? Deep tech requires a large amount of capital.
Mm.
So if the government gives that capital
Mm.
to build the infrastructure, then it's relatively easier for startups to really use these infrastructures and build something out of it.
And I think it's so important. Yes, it's like exactly what you said. Like, of course, the funding. If of course, if there are private fundings,
Right.
of course, it's always good. But if it is the governmental funding and from the city funding, it's much more easier. Decision goes faster, right?
Exactly.
And they kind of like connect that with all the different infrastructures that's happening, for example, around the city.
Right.
So it's much more scalable in that sense
Exactly, exactly.
compared to if there's a
Right,
private kind of
right,
funding for
right,
any kind of like
right.
projects like that.
And it's not just the infrastructure, it is also the ecosystem. You meet
Exactly.
like-minded people, you get all kind of help. So
Mm.
it really fosters that kind of mindset that yes, you have this amazing capabilities here. You can just come up with your idea,
Yeah.
test the idea, and be big.
Yeah. And what are you looking
Yes,
Aashish, in
so
here?
this is one of the room in this large clean room here. It expands quite a lot in the
Yeah.
back here. That's my favorite equipment at the back there. It's called a scanning electron microscope.
Okay.
So Gemini, it's written exactly.
Okay.
So this is another quantum, the outcome of a quantum physics.
Okay.
So electron, for a long time, was thought that it was a particle.
Okay.
And then quantum mechanics says it is a particle, but it also behaves as in a wave. So we use that property to image devices and structures at nanoscale, the scale that we won't be able to see with typical microscope, which is this one here, based
Yeah.
on light.
Yeah. Yeah, like a very look. I started to remember my science.
Right.
I also studied +2, like I did
Right, right.
science, and but well,
You wouldn't.
I don't exactly remember everything what I studied,
Yeah.
but at least I know that's a microscope. So.
Right, 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 exactly. So this you can see micro scale features, but with that you can push the boundaries down to nanometers.
Right.
Right. And then the another one there is called atomic force microscope.
Are we looking into
This
Gemini
from
or
this
Gemini or?
right in front of
Okay.
us, we are seeing the back of it.
Oh,
in
this
in the
one.
middle, in the middle,
In the middle.
Yes,
Okay.
yes.
Okay. Okay.
It's also $1 million, I think, from Oxford Instrument. And most of the equipment is like very expensive here. And there you can push the ability even down further to sub nanometer. So you have many companies here utilizing this facility. You have Dispelix, Semicon, IQM for a very long time was using this facility to develop their first products.
And then we cannot get in because we need to have like a
Yes,
proper
proper
dress,
gear.
and everything.
We can
right?
go from the front and
Yeah, for
look
sure.
at the whole
For
grounding
sure,
area.
for sure.
So this is called clean room because you don't want any dust particle or anything that can spoil the fabrication of your device. A single molecule, a single dust can really make defects in your structures.
Yeah, and we are talking about nano things,
Exactly.
right? And totally understandable. But yeah, and it's a lot of like expensive stuff in here.
Very expensive.
right?
Yeah, that's why government is pushing so much money and the city of Espoo so that they can buy all this infrastructure so people can just use it and not have to invest their own capital. And it happens so that in deep tech, investors don't want to spend money because they know most of the money goes into the hardware side.
Yeah, at the
right?
back. Yeah, exactly.
Yeah, and there's
Yeah,
very less profit compared to your typical software businesses.
Because I think with the deep tech, kind of like usually the investors are always like thinking about it because they have to put so much money
Right.
back all like later on also because like sometimes if you do a lot of iteration, got that money, if you kind of like start feeling like okay it's not working,
Right.
so you need more cash, more
Right,
kind of like
exactly.
money
Yeah.
in the company because that is the only way you can get more
Right.
hardware, for example,
Yes.
more kind of like more resources.
Right.
That means on a regular basis you are putting money after money, and
Exactly.
if they don't
And
see
you don't
any money
even
back,
know that it's going to pay back in
exactly
the long term.
data.
So
Okay.
this is where it starts. This is the first level where you put a face mask on and cover your hair, and then the blue thing you see there is to wrap your feet.
wrap your
Exactly.
feet, yeah.
And then you enter the next, area where the green gowns you see,
Yeah.
you cover yourself with those, and then there's after that a SU area where you put the clean shoes there, and then the door. I don't know if you can see it from here, next to the mirror on the left side.
Yeah.
That's where the actual clean room starts. So you have to take really precautions not to bring anything from the outside.
And they also have like a proper shoe in there
Right,
that you have to
exactly.
actually
Yeah,
put, right?
because people spend hours. Sometimes have spent tens of hours in the clean room in a single setting. So you need to have proper gear to last that long. VTT together with IQM developed the first quantum computer in Finland. First we got 5-qubit system, which is a much smaller system. Then we got like 20 qubits, and now they are changing it to 50 qubits. And qubits are the building block of quantum computer. The more you have, the more meaningful things you can do.
And you also mentioned off air that IBM has about 400 something or 500.
433 that is available to public. They are also building 1000-qubit system, which I don't think they have made it available to general consumer.
Okay. And IQM has like, I think, got almost like 350 million funding so far.
Wow.
And I mean,
That's
you know, they
brilliant.
have been, and of course, accumulated, they have like 4 million funding already. But
Right.
again, I'm sure Miko and the team is gonna go
Yeah,
and raise more and more, because
Right.
I think this kind of like stuff is definitely needed. And of course, Finland is pushing so much on also quantum computing and stuff. It looks like a, you know, I feel like I'm coming to a museum, like, you know, you're seeing so many, what has the developments been
Right.
in down the years.
And these are all the discoveries and inventions that have happened here at VTT. I'm sure you're familiar with ISI.
Yeah.
I think this is one of their product here.
They have also, I mean, you know, again, one of the darlings.
Yes.
Right?
Then the idea of these research centers are, of course, do the fundamental research, and if it has potential to develop some technology, then VTT provides this excellent opportunity to spin out companies from here. I think it's called VTT Launchpad.
Yeah, Launchpad.
Yeah.
Yeah. They usually have sort of like all these like smaller companies, and of course projects coming together, researchers coming together, and then, you know, again, you know, making that as a real company. And then there's a lot of like a spin outs also.
Which is the magnificent thing I've noticed here. Back home, you have universities where you just go there to get a degree. You don't really see research coming or companies spinning out from the university. And Aalto in particular has hundreds of companies coming out of their lab all the time. Okay, so we saw the first quantum computer, which is acquired with VTT. Then Aalto University itself is now establishing their own. And my colleague and my advisor, Suman, who is setting this up right now.
Oh, okay. But Blue Force is like, you know, is so important
Right.
because they are, I remember like they don't have any investors,
Right.
Looks like. And then they have almost like 190, I was like reading somewhere, like 190 million revenue.
Right.
And then that they provide this cooling system for quantum technology, right?
So it's also one of success story from Department of Applied Physics.
Yeah.
So they had decades of research in reaching low temperature to study the behavior of metals. And then later they found out, okay, you can do more interesting thing with this. Then they spun out the company, and they bootstrapped themselves into
Yeah, they bootstrap, exactly.
Yeah. And now they are world leading dilution refrigerator provider. They just set up a plant in New York, Syracuse, few months back. So now let's get back to when we talk about quantum computer. This is what we see. But this itself is not a quantum computer. The processor, the chip that I showed you in the office, that imagine is scaled up. That sits at the bottom of the fridge. This is the quantum processor as such. Like in our typical desktop, it's like quite huge, right?
Yeah.
But the CPU is the real computing that is there, right? The same thing here. And just to make that processor work, you need very low temperature. And that's what all this setup does.
Cooling system
Exactly.
and stuff. And also offline, as we talked about, for example, the bolometers.
Right.
How does it actually kind of like how they are connected with the, of course, cooling system and the quantum technology itself?
So detectors, as the name says, it detects some signal. So to do anything meaningful, you need to do operations on a processor, and you get some output. So right now, the output is converted into electrical signal that comes all the way out, and then you analyze that signal. It's based on current and voltage. So the detectors can just detect power instead of current and voltage. And it turns out if you detect power, you get more advantage. You get more what people call it fidelity, accuracy in the measurement. We are not there yet. Still, the best way is to measure the current and voltage, but the detectors have the promising advantage that if they can be designed in a better way, then it's going to provide huge advantage. So that's one of the research that we are doing in our lab.
Yeah, because I was also reading somewhere that I think Mikko was there, like when they were doing this, kind of like creating this kind of like a new sort of like a bolometers that kind of like I think he was talking about fidelity and something. Of course, I don't really know about those terms, but at least he was saying that that has been a very good research quite many years ago.
I can expand on that. So fidelity of an operation. So you do some quantum operation on your processor and you want to know how good is that operation. So that you measure with a so-called thing called fidelity. And as I said, either you can measure the signal by measuring the current and voltage, or you can use this detector. So for the very first time in the world, our lab demonstrated that you don't just use current or voltage, but you can also use power detectors to detect this signal and do the same thing. However, the results were not as impressive because we're just about to develop these technologies, and we have really ongoing efforts towards this direction. And once things really start to work out, then we might have the possibility to just remove all this out, really bring down the system to smaller level and detect signals in terms of power and not voltages. So it starts with the device, as we discussed. Then you fabricate the device. Then you want to know how does the device perform, and that's where the measurement comes in.
Okay. So all the equations, all the iterations, everything what you do there on the
boil
board,
down
on the
to this
computer
final
boils down to
moment
here, right?
when we start to measure the devices.
Okay.
As I showed you the clean room where we fabricate the device, once we are done with it, then we want to test the performance of the device, right? So after we put the chips in, I just put one yesterday.
And we are now, this is the Blue Force, right?
Most of the freezers you will see here are from Blue Force. Just the one we saw in the corridor over there.
So we put it down somewhere down?
Yes, somewhere at this bottom here. So you will see there are lines coming out, and these lines go down to the processor where you send the signals in, and then you measure what comes out. So once I put the new chip in, I want to know how does it perform.
Yeah.
So the first few hours every morning, as soon as I put my chips there, I look at the signals here.
Yeah.
This is a vector network analyzer. The frequencies we were talking about back there, that's what we measure here.
Okay.
So all these signals come out here, and once we detect signal at right frequency where we designed it, we're happy. The first few hours is very difficult for me, because if things didn't work out, then that means I have to redo everything for a whole 2 weeks before I can really measure anything and advance my research.
Okay, so you have to. So that means you have to be so precise, right? You have, because of course it takes so much time, and on top of that, so much energy.
Exactly.
Look at the wires, the amount of wires that are going through, the amount of electricity, the amount of the resources that it is using. So you have to be so precise before you actually put that on that thing.
Exactly. So we want to take all kind of precautions before really going to the measurement. We don't want to make any mistake because the feedback loop is so long.
That's true.
And can you hear this noise, pump noise? That's like 8 noise per second. Or per minute, actually. So people who come to the lab for the first time, they notice this, but I have learned to filter those out. So sometimes I don't even register them.
Yeah. All right. Man, as a kind of like a person who is not much aware of these kind of things, when you come here, it's like so overwhelming. From the machines to, for example, the equations on the board.
Yes.
It's like, okay, what's actually happening here?
And actually, the most important thing is this screen here. So if you zoom in to this display here, can you read what the temperature says there? 57 Kelvin. The first one there.
57
Kelvin.
What is that?
Kelvin is a unit measure of temperature. We usually use degree Celsius.
Okay.
So 100 degrees Celsius is 273 Kelvin.
Okay.
And now this is 57 Kelvin.
So it's like at a 25 degree or?
No, this is.
No.
This is minus 100.
A minus, okay.
Or not even 100. Okay, let me do a quick math. So 273 degrees uh, uh, Kelvin is 100 degrees Celsius. So
Okay.
50 would be around. Okay, I can't do the math right
Yeah.
now, but very low.
Yeah, very rough. Yeah, yeah.
Yes.
Okay.
And the temperature where the device operates, it is not showing the reading right now,
Yeah.
but it should be 10 millikelvin. Now
Okay.
that's like the 18,000 times colder than the coldest place on Earth.
18,000 times, right?
Right.
So imagine.
Right.
But again, at the end of the day, you can see in here the amount of resources in terms of course, people working for, working on this project, plus the money that spent setting all this up.
Right.
How much they are actually putting
That's
it
almost
there.
close to $1 million.
Only? We are looking at actually like almost 1 million kind of euro,
Right.
kind of like machine in here.
Right.
And of course, we can't even explain the quantum computer like IQMs and stuff.
Right. And so this is shared by companies and different research groups at Aalto University to maintain the expenses there. So my group, and then there are other research group at Aalto. Then Semicon is also using this same system. There is another spin out from VTT. They are also using this system to test their devices.
Okay. Okay. Wonderful.
Right.
But yeah.
Okay.
Aashish, thanks so much. I think we're still gonna go to your office,
Yeah,
and if
yeah.
you still have some stuff to show before we move into our main studio, right? Job as a postdoc, like doc, and also researcher is like a lot of going back and forth and looking into those machines.
And not only that, you also have to present your work at conferences. So this is my work that I presented in Corsica, France.
2021.
2021, just after COVID.
Okay.
This was the first time I could go out and present my work.
Okay.
It was a
Is Suman working in Blue Force?
Yeah, no, Suman is now a staff scientist at Aalto University.
Okay.
For some time he was working at, it was a postdoctoral
Okay.
university plus industry research work. So part of the time he was working at IQM.
Okay.
And Miko is the professor of VTT, and he has affiliation at Aalto, and he was the co-founder of IQM.
Yeah.
So you design you start with the physics, you design your device, you put them in the fridge, you measure your stuff, and you present the data at a conference. And I've been to Japan, I've been to Las Vegas in the US to present my work. I really like presenting the data at conferences. You meet like-minded people who are exploring something similar as well.
Yeah, and I think this is so important, especially what you mentioned like earlier, that the feedback from your research, sort of like let's say people around who are doing research on a similar topic, the feedback you get from them, and also probably get a bit more like what you actually need to do to go one step further, those kind of things, and you are always working on some iterations, and always some iteration has to be done on your
because
work,
this is something new. No one has researched this, so we don't know what the outcome is gonna be. So you start with something you know, and then you refine your knowledge based on what you have observed previously, and then you keep the cycle. It's called research, right? Search and search.
Oh, okay, I didn't know. That was a very good. I didn't know that.
I actually didn't come up with it myself. I saw a LinkedIn post by one of the scientists I saw, and then that made sense.
Okay, cool. And then I think that's all that we have here.
Right,
Anything you wanted to show at the end?
I think we're good. What I wanted people to see is the lab we are working on. It's a very expensive lab. We have the support from the universities. We have support from not just Finnish government, but also EU. We get this EU research funding that Miko gets a lot.
Yeah.
He's really good at attracting funding.
Yeah.
I myself have gotten funding twice, one from Kaute Foundation and one from Jenny and Antti Vihuri Foundation.
Our foundation,
yes. Towards my doctoral degree. The first one was I think 24,000, and the second one was 30,000 euros.
Okay.
So that is to pay my salary.
Yeah.
Even if I didn't have those, Miko's group funding would have supported my salary. But it's good to apply yourself and test your ideas that people are willing to give you grant for.
And there's always like sort of like so like the validity is also something that you would want to see, like of course that you as a single person you are applying for the funding, and somebody trusts the research that you are doing, so it's always a plus, always a positive kind of like a feeling on that one.
It kind of supports you that you're on the right track.
Of course. But I think it's so important, maybe like for for let's say from Nepal, Nepalese students, for example, people like who are watching from Nepal or from other countries who don't have this the level of quantum computing or level of tech that is already built for them to see how it actually works, to see a physical product is something that not many of them have the opportunity.
I'm also, I learn from seeing things and doing things with my hands, and it kind of puts an abstraction to something really physical. And by looking at, okay, what really is a quantum computer, you just keep hearing and hearing quantum computer, but you don't really understand what the whole thing is about. And then demystifying that can make it more accessible to people.
Yeah, exactly. All right, cool. Let's go to the studio. I'm very, very excited to have Aashish in our studio. Aashish is a doctoral candidate at Aalto University and has been working and researching in quantum computing for quite many years. So great to have you, Aashish, on the show. Welcome.
Pleasure to be here. Thank you very much.
Wonderful. Of course, Aashish, we're going to talk a lot about your journey in Finland, a lot about, of course, the quantum computing and that kind of like a scene. But maybe before starting that, a bit about like the Nepalco journey. How has it been? How was there? A bit about, kind of your childhood plus also a bit about your own professional journey. Alikati त्यसको बारेमा भन्दै हो, if you could share.
Yeah, sure. So I was born in Janakpur. Family of 4, mom, dad, and a lovely sister. I did my education until 10th grade in Janakpur, and then usually is the trend that you go do high school somewhere else. My choice was either stay there or go to Kathmandu like many other students. I decided to go to Kathmandu. Part of the reason was to, be able to live independently. And my best friend at the time, or even now, also was deciding to go to Kathmandu, so I didn't want to separate from him. So that's how I ended up in KTM, and then I initially started taking these coaching lessons for high school entrance examinations. However, I didn't end up doing typical +2. I chose to do this A levels, which is the high school degree given by University of Cambridge from the UK.
And Aziz, what year are we talking about?
This is 2010 summer.
Okay. Yeah.
And then I started my A levels around, I think, August or something. Yeah. And that was a funny story. So lately I've realized that all of my major decisions in life, I have gotten them in some sort of advertisement from newspaper or either YouTube.
Okay.
We'll get to that in a while. But yeah, I was reading, I think, the Kathmandu Times or Post, I don't remember exactly. And there was this advertisement about entrance exam for A levels from Chelsea International Academy. And it was at one of the biggest hotel. There was buffet and cakes and whatnot. And I think, okay, that should be interesting. I could just go and appear there and see what it's like.
Yeah.
Didn't practice for the exam at all. And then went there. Questions were pretty easy. And then turned out that I got accepted. And that's how I ended up doing A levels. And then towards the end, most of the students were deciding to go abroad for further studies. And I spent a couple of years applying to the colleges in the US. And then I saw the news and I wanted to just apply there as a safety net. So I went there again, unprepared, took the entrance exam. And I got accepted there as well.
What kind of question do you remember? Like what kind of usually like maths and English and those kind of mixed?
True. Yes, math, physics, chemistry, and biology.
Yeah.
Pretty basic stuff.
I think it also depends on which stream are you applying for.
Oh, maybe yes, that's true. That's true. So I was applying for science and engineering. So yeah, that was mostly for safety net. I initially wanted to go to the US, like many people, many of my friends, and then after receiving the acceptance from some of the university in the US and also also from Finland, I had to make a decision. In the US, I think I had gotten 50% of the tuition fee, so I had to pay around 10K per year.
Per year, right?
But on top of that, you also have to pay for the living cost.
Yeah.
So that seemed a bit expensive. However, in Finland, if you get accepted, then there was no tuition fee at the time. Now that has changed. So that seemed financially easy decision to make. Yeah, so then I chose this Hamk Amatti Korkeakoulu, which
Hamelin.
Hamelin, in Riihimäki actually.
Ah, Riihimäki.
Yeah,
Okay.
so that they offer a mechanical engineering degree.
Okay.
Right, so that's how that was the
Journey.
journey to
Journey
Finland.
from Nepal to Finland, eh?
Okay, in Nepal, I did when I was applying for the universities. I was teaching maths at Chelsea to eighth grade. That was a very nice experience. Also to get some money, so I didn't have to ask my parents for that, and also to explore if I'm good at teaching or
Yeah,
not.
and I think, and that is the same place where you did your A levels,
A levels,
right?
that's
So I
correct. Yeah.
think graduating from that school and also giving back to, for example, the same community should be really good. Also, yeah, I think you also did some volunteering roles
That's
on
true.
some noble
Right.
areas. For example, I read your LinkedIn profile, and you mentioned there like you were also working as orphan in the orphanage home, and also recorded some novels and books
Right.
for blind students. If you
Right.
could tell a bit more about
Yeah.
what are those,
Right.
how did it kind of opportunity came about, and
Right.
kind of like what motivated you in the first place
Yeah.
to do those things.
Well, to be honest, it was mostly for a selfish reason because it would look good in college applications. However, as I started doing it, I really enjoyed it. So I chose two places. One was Nisaya Briddha Ashram, I think, somewhere in Baneshwar. And our job was to, I with a couple of my friends, we went there and asked if we could help. So our day-to-day job would be to warm water for them so they can take shower and whatnot and help them set the beds. And then you get to talk to all these people who are living together and then sharing their life experience. And we were quite young back then, so very young teenager, ambitious teenager talking to the really experienced people, and that kind of was quite change in pace of things what we were on our daily life consuming and then what they had to give. So in that regard we got some valuable lessons ourselves. And then the recording the books, my best friend Sif, we found out that place that okay, it's a cool opportunity.
Yeah.
I always wanted to know how I sound in recording. So, and also you could get to read books.
Yeah.
I think I chose some English novels to record for blind people, so they could listen to whatever we have recorded. It took us few rounds to really get nailed down the whole book. Uh, Back then, I would speak so fast, like all the Nepali students, because you had to, if you take time or pause, that means you don't know English. That was a misconception back then. Um, and yeah, it was a noble cause, and I'm glad that I did it. It
Wonderful,
really, yeah.
wonderful. I'm sure that helped up, kind of like also giving back to the community is something I think in all of us that समाजको लागि केही गरौँ कि भन्ने कुरा चाहिँ feels. I think everybody has it. Now maybe moving on to the career path. Of course, you mentioned a bit about coming to Finland. What about the technology stream itself? Do you remember those times that when did you feel that okay, your science, भनौँ tech that is the area that I want to study or pursue my career? Is that something that you had
Yeah.
remember any of those incidents when you decided to
Not
choose?
immediately when I came to Finland. It was very traditional courses. I had been familiar with all the tools that were being taught at the school, like CAD software to design any mechanical components. So in that sense, no. But my journey didn't stop there at HAMK. After studying for 2 years, I decided to quit. I really didn't enjoy. It was really applied, and I wanted something theoretical, which really gets into why things uh, behave the way they do. So I decided to apply at Tampere University of Technology. They were the first Finnish universities that were offering bachelor's degree in science and technology in English. And that seemed to me, the day I found out about that, I was like so happy. I shared with,
That you need to apply,
yeah, yeah, and then
right?
I shared that information with my friends, and two of my friends who were in the same degree at HAM, they also decided to apply, and we all three went there. And there, first time, I found out about pattern recognition and machine learning, one of the most powerful tool that people use to build AI technologies. And then there I started getting familiar with cutting edge technology. And I think that kind of sparked interest in me to pursue that in that direction.
Hmm. And also looking at your own journey, Asis, I think, like you've been a teacher in Nepal, and Zuni, from 29, I think 2017, you've also been involved with Tampere University as a research assistant. You've also taught there, especially in the quantum computing part. How did the overall, maybe like, the important question for all of us is, what is quantum computing in the first place, and maybe following up on that, what are the applications, like why quantum computing is so important in today's generation? What are the applications? What different industries can it be applied to? If you could tell a bit
Yeah,
more about those things.
yeah. I mean, before we talk about quantum computing, let me walk you through my journey
Yeah, yeah.
to this field. So I was in Tampere, and I liked teaching because it was again for a selfish reason. Richard Feynman, I think, he said, if you can explain it to others, then you know understand the field, and that was the motivation, and of course the monetary as well. At the time, I think I was working as a paper delivery boy and or cleaning as well to support myself here. You need to either have I think around 7K back then to renew your visa, which was yearly,
Yeah, we
and that
had at our time, I think
right,
6K was the time.
right, right,
6K was the amount.
right,
But of course, like as the year
and
goes on, you have like more and more. You need
right.
to prove a bit more.
Yeah,
Yeah.
and then the hourly rate was really impressive. I think it was 30 euros per hour. So I thought, okay, I can kill what two birds with one stone. I get to teach and also can secure funds for myself. Just after my first years of education, one of the teacher who taught physics asked me if I can TA his courses because he liked my performance there. I said, sure, why not? And then I started with teaching physics fundamental courses, and then continued to develop interest in AI. So I started working as a teacher and teaching assistant in pattern recognition and machine learning, artificial intelligence, helping the teacher really develop the course. So then the interest from Nepal, when I was teaching maths at to the 8th grade, I think
Mm.
I found out that I like it and I was good at it. So I continued doing it from there. And I think in 2019, just before pandemic, I had to decide for a topic to finalize my master's thesis.
Mm.
And my current supervisor or a supervisor back then didn't have enough funds, so he suggested me to find a place that can give you some money as well for the thesis. It was very noble from him. Most people would just ask you, okay, you can do it for free. So then I started looking for options. And I think this is the third decision that I found from another ad, or let's say YouTube video, that got me to quantum computing. There was a video from Mikko's Mottonen lab where I'm doing right now my PhD. They were jumping into this lake in freezing minus 20 degrees temperature, and they were trying to explain the concept of quantum circuit refrigerator. And that seemed really interesting to me. Okay, there is this device that can physically cool down a quantum system, and so the researchers were investigating these quantum devices, and I thought, okay, I can work on this for my master's thesis. So I immediately contacted him, and he's the guy who likes good grades. So I had good grades at Tampere, and he immediately contacted me
Okay.
and then said that we have a master's thesis position for you if you're interested.
Nice.
I also had gotten a couple of offers from, I think, some camera developing company. I don't remember the name exactly. So then again, I had to choose whether I go there or stay in Tampere. But usually, what happens to me is that if I keep doing something for a long time, I get bored. I want to do something new, and that seemed like a perfect opportunity for me to start. And that's how I got into quantum computing field.
Mm.
Now, coming back to quantum computer, what are they? This is a new way to computing. Um, so right now, classical computers are based on transistors. They are like switches, which can be turned on or off. If it's turned on, that represents a bit 1. If it's turned off, then you have bit 0. And then you can put billions of them, and that is what requires for modern phones and computers to perform really large scale calculations. And these transistors are physical devices. They are so small now that it it is approaching a subatomic limit where quantum effects start to kick in. That makes calculation unreliable and unpredictable. So we need some fundamentally new way to make computers.
Yeah.
And quantum computers can do that. So as I mentioned, bit 0 and 1, computer works on qubit that can be 0 or 1 or both at the same time. This is called the principle of superposition. And it turns out that it allows you to solve certain problems which are intractable, meaning very difficult to solve on a classical computer, to do it very efficiently and at a very short time scale. Of course, building the quantum computer is a challenge in its own, which currently industries and research labs are trying to explore. So that's what a quantum computer is. It's trying to encode information on a fundamentally different technology to give us that extra advantage that classical computers cannot do right now. And it is expected to provide significant advantage in drug discovery. So problems that require simulations of atoms or molecules, they behave with the laws of quantum physics. So it turns out if you simulate them on a quantum system, it's very efficient. And then people have also realized that you can map the problem of finances. So imagine you have to find a right answer among many different possible outcomes. And it turns out quantum computers can do that efficiently. And then you have cryptography. All our current encryption system are based on integer factorization. And if a quantum computer can do that quite efficiently, a classical computer would take millions of years to break current encryption system, whereas a fully large-scale quantum computer can do that in a minute.
I mean, the amount of time that it takes is
Yes,
so. I
right.
mean, it does so fast, exactly
Right.
like you mentioned, and that it can be applicable in so many different industries,
Right.
making it much more faster, much more smoother, and much more accurate. I think, right?
Right. Yeah, that's true. Accuracy, even classical computers gets you that. It's the time of computation is what the advantage you get. Having a quantum computer itself is not enough. You need to be able to write algorithms that can efficiently use a quantum computer to solve the problem.
That's true.
And there are only a handful of algorithms right now. So, for example, Source algorithm is a very efficient way for factorization. It's a proven method that you can implement if a quantum computer is available. So it can help encryption system straight away. Simulation of atoms and molecules, again, same principle. People right now, they're like Goldman and Sachs and all the other financial institutions are investing heavily on quantum research right now. To really understand what kind of problems they can solve with quantum computers. So right now we're mostly in exploration stage, whether we can use it or not. But the research shows that it has really an advantage in that domain as well.
And we have also, I mean, kind of visited. We also visited your lab and the workstation that you have, and also went through, for example, looking into the supercomputers and all the cooling system and stuff. It really shows that Finland is really putting a lot of resources in terms of not only researchers but also like really finances also in terms of financing also, because we have like this IQM, Blue Force, and all the VTT spinoffs and those things. So that definitely shows there's a good kind of like a really bright future in terms of quantum computing and the research space.
Right. So this is actually a very good story. Whenever I go on conference, especially from American colleagues, I get often asked, Finland is such a small country. How come they are so good at quantum technology? And that has to, then that is because Finland adopted this low temperature physics at a very early stage. It's already in 1965. Back then, Helsinki University of Technology. Now it's an Aalto University where I'm doing my PhD. They were investigating metals at a very low temperature where they behave like a superconductor, and that allows you to make a quantum computer, which we showed you today. So, given the decades of research, kind of put them at the forefront of this quantum technology. So, they were fast enough to get into the field and reap the advantage, and that is what is allowing them to really stand out in this whole in the whole world.
What about this Lumi
Supercomputer,
supercomputer
yes,
that's
right,
being quite popular? It's like one
right.
of the
Second,
fastest in
I,
Europe, I know.
yeah, it's definitely in Europe, but I think it's even in the world one of the second largest
Yeah, yeah,
supercomputer.
and it's built in Kayani because the
Guyana, yeah,
resources, of
right,
course, like probably much more cheaper and kind of
right,
like I think the sort of like overall infrastructure
yeah,
is set in that way,
right.
right?
Because there are so many computation going at a time that the devices heat up and you have to
Mm.
cool them down. And Kayani is a really cold place,
Yeah, yeah.
so you can really use the climate there to efficiently cool them down. So now that's a supercomputer, not a quantum computer. It's a classical computer stacked in large areas, sorry, in a large setting, which allows you to simulate many jobs on a different computers and then combine the results later on. But Lumi also provides, I think it's a Helmi part of, or maybe in the same domain,
Mm.
that allows you to access Finland's first quantum computer, which we showed you today in the
Mm.
VTD premise. So researchers can log in to their cloud-based system. If they have some specific problem on their mind, they can program them and send the job to the VTD. Yeah, and then they can simulate what not simulate but run the actual job there
Okay,
and get back the results over the cloud.
okay.
And that's how I think the future of quantum computers. You're not gonna have a quantum computer like a laptop you have in your home. It's gonna be like a data center, like supercomputing centers, where they are tucked away somewhere far where people are not there, and you you will mostly reap the advantages uh, on your own computer or a mobile phones.
Interesting. Also, in terms of course, you have been involved in the research for quite many years.
Yeah.
Aziz, do you kind of like remember any memorable sort of like findings from
Right.
your side that you felt like, okay, we've done
Yeah.
something in
Yeah.
terms of it doesn't have, I don't know if it is a breakthrough
Right.
kind of like a
Right.
research that you have done, but
Right.
something that you're kind of really proud of, or that you can say like, okay, this is something we have did
Right.
really interesting one. If you have any kind of like a
Yeah. Definitely.
example.
It happened this year actually, which resulted in my first paper as a
Okay.
first author. So we were looking into this qubit, which is a building block for a quantum computer that implements a quantum bit, just like a transistor implements a classical bit. Um, and in order to do any sort of processing, you need to be able to control this qubit. And it turns out to control this qubit, you have to talk with the environment. The qubit needs to talk to the environment, which necessarily impact negatively on the performance of the qubit. So there is this trade-off where you need to be able to control the qubit, but then also that represents losses in the system. Then in my research, what I did was find a way that you're able to control, but because of that control, you do not make the calculations or operations on the qubit
Mm.
bad.
Okay.
And yeah, it was one of the new ideas that we were exploring, and it kind of we published the results in a Nature Portfolio journal in communication physics, which is one of the well-respected journal there.
Wonderful. Congratulations
Thank
on
you.
that one. Since we are still on this topic, Ashish, is there sort of like, any, potential applications or kind of like that you're excited about? What's the future of quantum
Yeah.
computing, or what the future of the area that you're working on?
Definitely. I'm a quantum physicist, so for me, simulation of physics is the most important one. But besides this, I also have a background in AI, and you could use quantum computers to for training a model or something like that. Um, Besides that, I think the exploration stage is what really is very interesting to me, because you are now trying to look in the dark what you can do with the quantum computer, and imagine finding something in the dark. The kind of joy you get is just something really overwhelming. So we don't know what a quantum computer can do, but then the possibilities are unlimited.
Absolutely, absolutely. I think everybody, like looking into this field, from the investors to the startups to the researchers themselves, they are looking for what new breakthroughs out of innovations can be taken out from here, and of course, the limitless implication of quantum technology itself in those industries. I think everybody is excited on that one. Maybe the last kind of like a pretty much in the last kind of like a section that I wanted to ask, for instance, in terms of quantum computing itself, for us, for many of us, many generalists, we kind of like directly think, okay, it's a very, very vast, very, very, kind of like advanced topic. What do you suggest for anyone, for example, watching the episode today, that if they want to get into this field, what do you think are some of the important aspects they need to look into?
Yeah, that's a great question. Now that depends in what phase of your career you are. If you want to pursue in research stage or industry, then that the answer would depend. But what I would suggest is to look into what. Okay, can we redo that again? Um, right. The thing with quantum computing is that it's a very diverse field. You need electrical engineers, you need computer scientists, you need semiconductor technology experts to come together and build this technology. So it's quite diverse. Um, you can transfer skills that you have learned in another field to come and work in this. You need to do a little bit of homework, find out what are the sectors or verticals in quantum
Yeah.
computing that you want to work on. And it has to align with your skill sets and with your ambition and goal. And then you can really contribute in the development of quantum computing. And I think conviction and dedication, these two things, most of the time they sound similar, but conviction is the belief in certain technology or believe in something. But for me, what matters is like, yes, I believe quantum computers has the possibility to do really useful things, and that allows me to dedicate my time, my energy
Mm.
into solving problems.
Mm.
So find what is your conviction, and then find what kind of skills you want to dedicate your time to.
Yeah, and also like what you mentioned in terms of what kind of verticals that you are
Right.
interested in,
Exactly.
especially in this
Right.
industry, right?
Right. It can be a software side, it can be a hardware side, even in the marketing side. There are tons of different opportunities. I would recommend this book by Robert Schutor, Dancing with Qubits, and he is very nicely laid out all the verticals there. And you can go through that book. And even if you have never heard of quantum computing, that's a very nice place to start.
Wonderful. Thank you, Ozzy, so much for sharing your expertise and, of course, like sharing your experience and your journey in the academic world, especially to our audiences. So any last words that you want to share with the audiences watching this episode?
Yeah, definitely, especially audiences in Nepal. Look into this field. This is going to be the future. And if you want to stay relevant, already understanding this now is the time.
All right. Thank you, Asi, so much
Right.
once again for being part of the episode. And to everyone watching the episode, all I can say from my side is stay inspired, keep on grinding, and keep on pushing boundaries to reach new heights.